Okay. Recording team. Okay. Okay, good morning. So let's continue our learning. So we have started learning about MRAM technology. Yesterday I discussed about how do we write information in MRAM. So writing is basically switching the magnetization of the free layer. So if we switch the magnetization of the free layer parallel to the, maybe we will do a recap of what we learned today, yesterday. The reference layer magnetization is always fixed in one particular direction. So writing 1 means making the free layer magnetization to be anti-parallel to the reference layer. Writing 0 means making the magnetization of the free layer to be parallel to the direction of the magnetization of the reference layer. Okay. So this is basically writing. So since we are switching the magnetization, we also use the terminology switching to represent writing information. So I taught you a few techniques to achieve switching. The first concept that we learned is using magnetic fields generated by current carrying wires. Okay. So in this particular case, we have two wires. Let us say there is one current carrying wire this way, let us call it a bit line. Then there is another wire, let us call it a right line. So another current carrying wire. The MTJ that you want to switch is somewhere here in between the two wires. Okay. Let us say this is at the bottom. Let us say this is at the top, the MTJ is in between these two. So when you send current through the two wires, you are producing orthogonal magnetic fields. Okay, so these two fields are in an angle of 90 degree with respect to each other. So one of the, let us say one field is parallel to the EZ direction, let us call it EZ H. Okay. So what this field does is, I mean, in the absence of any magnetic field, we have this kind of energy landscape. Okay, so we have EB, which is KUV. So we have two EZ directions. When you apply magnetic field in the EZ direction, it changes the energy landscape a bit. So the energy barrier is reduced now. Okay, so when you apply magnetic field in the hard direction, the hard direction magnetic field reduces the height of the energy barrier, is smaller now. Okay, so just one magnetic field cannot switch because these magnetic fields are not large enough to change the energy barrier landscape completely. Okay. So by using these two magnetic field together, then we can exceed the energy barrier and we can switch the magnetization. Okay. So this is the technique used to selectively switch MRAM. Okay. So only the MRAM, the MTJ cell which is in this intersection will be switched. All the other MTJs along this line or along this line, they won't be switched. okay, because they feel either this kind of energy landscape change or they only see this kind of energy landscape change. So, there is still some energy barrier. So, none of these MRAM MTJs will not switch, none of this will switch, only this particular MTJ will switch. Okay. So, this is one concept that we learnt yesterday. Then the second concept we learned yesterday is STT switching, spin transfer torque based switching. So, to understand this one we learnt, we recapped the concept of angular momentum transfer. So, spin, magnetization, all are angular momentum. Okay, so, there can be angular momentum transfer between spin and magnetization. The second concept that we learnt when we talk about spin transfer torque is spin polarization. So, for example, if you take a copper wire, you send electrons, almost equal number of spin up or spin down electrons will come out. Okay. So, there is no difference in the number of spin up or spin down electrons when you send a stream of electrons through copper. Okay. On the other hand, if you send a stream of electrons through a ferromagnetic materials magnetized in one particular direction. So, in this case, the number of electrons that have magnetic moment in the same direction as magnetization will come out more in number, and the spins with opposite magnetic moment will come out fewer in number. Okay. So, this aspect is called spin polarization, and we are using this property to switch the MTJ. Okay. So, if you have a reference layer like this, spacer, then free layer which has anti-parallel magnetization, and let us say you send a stream of electrons through this layer, and if these electrons are majority in number, they will exert a torque on this magnetization. So, finally, these two will become parallel. Okay. So, we call it AP to P, anti-parallel to parallel switching. Okay. So, remember that torque will happen only when there is a component perpendicular to the magnetization. Okay. So, either the spin should have some component along this direction which is perpendicular to the magnetization, or if spin is like this, then this magnetization should have some component. For example, if the magnetization is like this, then there will be a horizontal component which is perpendicular to this spin. Okay. So, torque will be non-zero only when the spin, a component of spin or magnetization are perpendicular. So, I was always showing spin up, spin down electrons going this way, and this magnetization also is perfectly parallel. Okay. So, you may wonder how it can switch. So, when these two are completely parallel, there cannot be torque, there will be no switching. So, what happens when you operate MRAM, for example, first of all you are operating at room temperature. So, there will be thermal fluctuations. Secondly, you are also sending current, there will be some Joule heating. So, maybe you even go from room temperature to slightly higher temperature, let us say 80 degrees Celsius or something like that. Okay. So, this temperature will make the magnetization to fluctuate. Okay. So, this free layer magnetization is not completely parallel to the spin magnetic moment because of the fluctuation. So, it may be rotating or something like that. Okay. So, at some point of time there will be some horizontal component. So, on this component the spin magnetic moment will act, then you will have switching. Okay. So, this point I missed yesterday. Okay. So, this is one way of switching, and if you want to switch from parallel to anti-parallel, you just reverse the direction. Okay. So, the electrons that get reflected from this interface go and switch the magnetization from parallel to anti-parallel. That is second concept that we learnt. The third concept which we learnt yesterday is spin orbit torque MRAM. So, in the case of spin orbit torque, we are looking at let us say we have a nucleus, electrons are going around. So, from the electron's perspective, it will appear that the nucleus is going around the electron. So, there will be a magnetic field. Okay. So, that magnetic field and the spin interact. Okay. So, that gives rise to the spin orbit coupling, and because of that we have the spin Hall effect. That means, if you have a heavy metal layer and you send a current through the heavy metal layer, okay, one type of spin will come up, then in the bottom side you will have the opposite sign. Okay. So, we can use these spins. Let us say we have another ferromagnetic layer on top. So, we can use these spins to exert torque on the magnetization of the ferromagnetic layer and switch MRAM, switch the free layer. Okay. So, in STT MRAM typically the heavy metal is at the bottom, then free layer is at the bottom, we have magnesium oxide, reference layer is at the top. And we need 3 terminals. Okay. So, we have one terminal, I mean 2 terminals for sending the writing current. Okay. Then for reading we use another path. So, we have a third terminal through which we send current and we read information. Okay. So, this is the reading path. And this is the writing part. Okay. So, because of this we have some advantage. I told you that writing current is larger than the reading current. So, in the case of SOT MRAM, so we are sending the larger current through the heavy metal. So, it does not go through the magnesium oxide. So, it does not break down the tunneling barrier. So, in the case of STT MRAM, tunnel barrier breakdown TBBD is a problem. It is a problem in STT MRAM, but it is not a problem in SOT MRAM. Okay. So, these are some concepts that we learned yesterday. With this recap, let us move on to today's topic, which is about what are the research work that have happened in the aspect of storing information. Okay. So, we finished writing, we will discuss about storing today. Okay. So, as far as storage is concerned, you know that the energy barrier is the one that helps to retain the information, and the energy barrier comes from the magnetic anisotropy. Okay. So, you learned that KUV is the energy barrier that helps to retain the information. So, this Ku can come from materials. For example, you take iron platinum, L10 iron platinum. So, this material has anisotropy of the order of 10⁻⁷ per cc. It comes from the magnetocrystalline anisotropy. So, it is a material property. On the other hand, if you take say cobalt, platinum multilayers, so here the anisotropy is coming from the interfaces. Okay. So, any anisotropy is okay. So, as long as there is an anisotropy and the material has certain volume. So, in the case of MRAM, this volume is basically the cylinder's volume. So, we are having devices in the form of cylinder. So, you know the diameter, you know the thickness, you can calculate the volume. So, this volume multiplied by Ku gives rise to the anisotropy energy, and that is what helps us to store the information. Okay, so, this one we have seen many times. So, based on how do we store information, we have two types. One is called in plane MRAM and another is called perpendicular MRAM. So, if you remember when I taught you the magnetic recording, I told you that there is something called longitudinal magnetic recording technology, where the magnetization in the recording media is parallel to the disc. Then we did not learn the perpendicular recording technology, but in the perpendicular recording technology I told you that the magnetization is perpendicular. Okay, so, we use almost similar concepts. So, in hard disk technology, this longitudinal recording technology was used from 1956 to almost 50 years it was used. Then somewhere in 2025, the perpendicular 2005, this perpendicular recording technology came into picture. So, in a similar fashion, in MRAM also, in plane MRAM was the oldest technology, and perpendicular recording technology is the newest technology. So, you may wonder why we did not start with perpendicular MRAM right away. Okay. So, we know that perpendicular recording technology is better. So, we should know that perpendicular MRAM will be better. Why we did not start right away with the perpendicular MRAM, why did we do this? So, you will learn that today. Okay, let us first start with in plane MRAM. Okay, the first reason is like why we start with in plane MRAM in the beginning at all. Why do not we start right away with perpendicular MRAM? It is because of the reason which I have told you many times before. The hard disk technology is the pioneer of Spintronics technology. So, almost everything except spin orbit torque comes from the hard disk technology. Okay. Until the spin transfer torque, everything comes from the hard disk technology. Okay. So, in hard disk technology we use readers. Okay. So, we learnt about TMR readers, tunneling magnetoresistance readers, which looks exactly like this. Okay. So, you have a pinning layer. So, this magnetization is pinned at certain angle, and you have a free layer whose magnetization is perpendicular to this one, and we are using the magnetization direction of the free layer to read information, right. So, when people were working on this concept, they thought, okay, we should try to make memory out of the same TMR or GMR devices that we are working on. So, that is the reason why the MRAMs of the earlier days were of in plane types. Okay. So, it basically is like a spin off. So, you do this one, but you also try to use the same sensor design for MRAM application. So, that is one reason why the most of the early generation MRAMs were of in plane types. Okay. So, here we are talking about storing. So, we can store the magnetization in at least two different ways. Okay. One is like the two layers are parallel to each other. So, resistance will be low So, if you send a current through the device, you will find that the voltage is low. Okay, you can call this as 0. You can have another state where the two magnetization are parallel. So, if you send current through this device, you will find high resistance. So, you will see a large voltage, you can call that as 1. Okay. So, these are the two states of storing information. So, you may argue that we can have like the two layers orthogonal, all those things. You can have maybe intermediate states, but it is useless. Okay. We do not have that much change in the TMR between these two states. So, people are happy with the just two states as of now. Okay, so, as I mentioned yesterday, the reference layer has so many names. Okay. So, I may use fixed layer, sometime I may use polarizing layer, pinned layer, reference layer, hard layer, all these layers refer to this layer whose magnetization direction is always fixed. Okay. So, this layer is called with so many names, and the free layer whose magnetization can be changed to be parallel or anti-parallel has a few names like this. Okay, so, I mean the key point here is that in plane MRAM, the magnetization is parallel to wafer. Let us say you have a 12-inch wafer. Okay, so, the wafer will look like this, I mean circle 12-inch. The magnetization is parallel to the wafer. So, that is the in plane MRAM. Okay, so, in plane MRAM usually uses soft magnetic materials like cobalt, iron, boron. Okay, the reason being, as I mentioned, this is an extension of read sensor projects from hard disk industry. So, they have been using this cobalt and boron. So, they just stick to the materials used for read sensor. And the second reason why we use the softer magnetic materials was because at that point of time, let us say people are doing this research in 2000 or earlier, we do not have the concept of using STT to switch magnetization. So, we were relying on the magnetic field assisted switching. Okay. We learnt about magnetic field assisted switching. So, we relied on this switching method. So, if you want to use high anisotropy materials, then the current you require to switch was a problem. Okay. So, because of these two reasons, the in plane MRAM community, they always used cobalt and boron. So, in this particular technology, as I mentioned before, we pin the magnetization direction of the reference layer with a pinning layer, which is an antiferromagnetic material like iridium, manganese, for example. Okay, so, that is the second point. The third point, yes, we use exchange bias. So, I gave you this recipe. So, we use a magnetic field and anneal the ferromagnetic antiferromagnetic stack. Okay. So, this induces one easy direction. Okay. So, this is the third step. And the fourth reason is like in 2000, people were not aggressively looking for small MRAMs. So, for large size MRAMs, cobalt and boron was okay, no problem. Okay. So, because of all these reasons, people used materials like cobalt and boron. Okay. So, this you have already learnt. So, we are using the interface anisotropy which is also called unidirectional anisotropy, to pin the magnetization direction of the reference layer. So, we have iridium manganese as the antiferromagnetic layer and cobalt iron boron as the free layer, and we follow the recipe that we learned earlier. So, we apply certain magnetic field, heat, anneal the material over a temperature which is more than the anneal temperature, let us say. Then after we cool down, we will have unidirectional anisotropy, which means the magnetization will be always at one particular direction in the absence of any magnetic field. Okay. If you apply high magnetic field, you may be able to switch, but once you remove the magnetic field, you will always end up here. Okay. So, this is the concept we used in the GMR sensor, and we use the same concept in plane MRAM also. Okay, so, why we need to do pinning? Why do not we just have a layer without pinning? So, that is explained in this picture. So, we are talking about field assisted switching. Okay. So, in field assisted switching, we learnt that we will apply two magnetic fields, right, one along the easy direction, one magnetic field along the hard direction. So, by applying two magnetic fields, we select the MRAM that we want to switch, right. So, this means that the MRAM or the MTJ you make should have an easy and hard direction. So, it should have easy and hard directions. Okay, let's take this plane. Okay, so the magnetization is along this plane. Okay. So, how many directions are possible for this magnetization to be along this plane? 360 degree. Okay. So, the magnetization easy axis can be in any direction. So, the easy direction can be 0, 90 or any angle between 0 and 360. Okay. So, in the case of in plane magnetization, the easy direction can be anywhere between 0 to 360 degree, but in that case we cannot know where is the easy direction or hard direction. Let us say you have wires like this, and we think that this should be the easy direction, this should be the hard direction, but if the MRAM below has any easy direction in any angle, we may not be able to switch the MRAM. Okay. So, to define the easy axis and hard axis, there are two possibilities. Okay. So, one possibility is you can use shape anisotropy. Okay. So, if you make elliptical bits, so you can say that easy axis are along this direction. So, this is the hard direction. So, this is one possibility. We can use elliptical bits. Okay, elliptical bits have shape anisotropy, but the problem is the area occupied by elliptical bits will be larger, right. Let us say this is the minimum feature that you can achieve with let us say f is the minimum feature that you can achieve with a lithography technique. Okay. Then this, I mean the diameter on the other side is like 2 f. Okay. So, the area of your elliptical bit is going to be larger. Okay. That means you cannot pack more bits in a given chip. So, we do not desire elliptical bits because they occupy more area. So, we want circular bits. So, as I mentioned, the circular bits can have easy direction anywhere. Okay. So, they do not have shape anisotropy. There is nothing to fix the magnetization direction of these bits along any particular direction. Okay. So, this is the reason we use the antiferromagnetic material and do the magnetic field annealing technique to induce magnetization in one particular direction. Okay. So, let us say we deposit the ferromagnetic material on top of antiferromagnetic material and we apply a magnetic field along a particular direction. Let us say in this case, okay, this is my wafer. During the annealing process, my magnetic field is along this direction. Okay, I cool down. So, after I cool down, all these small cells that you have, they will have easy direction along this direction. So you can set the easy direction by doing the field annealing process. So, this way you can have circular bits with easy direction all along one particular direction. Okay. So, that is why we need the AFM antiferromagnetic material in plane MRAM. Okay. Yeah. Okay. Why do we use high temperature for? I mean, we are operating MRAM devices at room temperature. So, the pinning should happen at room temperature. So, low temperature pinning is useless. So, we want to have pinning at room temperature or the operating temperature of MRAM, that is one thing, but we are annealing at high temperature to achieve the pinning effect, right. So, the annealing at high temperature is to ensure that you go above the anneal temperature. So, your antiferromagnetic material okay, to start with, your antiferromagnetic material itself may have domains. Okay. So, within this domain, let us say these are the anneal vectors. So, what happen if you zoom in here? So, that region, the magnetization of the neighboring spins of antiferromagnetic material will be antiparallel. So, all this will be there. Okay. So, during the annealing process, what you do, you apply a high temperature more than the anneal temperature. So, thereby you make the antiferromagnetic material to be a paramagnet. So, at this point of time, you apply certain magnetic field. So, this magnetic field is forcing the magnetization of the ferromagnetic layer on the top to be along certain direction. Okay, now you cool. Okay, now you cool the whole system, ferromagnetic antiferromagnetic layer sandwich. You cool down. So, when you cool down, now you may not have these domains. Okay, all the antiferromagnetic spins will be, I mean at the top they will be aligned with this magnetization. Like this. Okay. So, you need to heat at a temperature above Néel temperature. Okay. So, I mean quite often researchers do not bother about temperature. So, they say they observe some phenomena at 30 Kelvin. 30 Kelvin phenomena is useless for technology. So, when we are talking about technology, so we should be constrained to work on the limitations set by the industry. Okay. So, whether you make say some semiconductor chip, the temperature during some process will go even as high as 300 degrees Celsius. So, whatever material you make should be able to withstand this temperature. Okay. So, if you have material that does not tolerate 300 degrees Celsius, that material is useless. Okay. So, you can publish paper, but if you want to use something for technology, you have to play the game according to the rules. Okay. So, there are many requirements. So, your material design has to meet all the requirements. Okay. So, making a product is not easy. Okay. Doing research, you can do anything. You can observe some phenomena at 3 millikelvin and you say that it is very interesting. Okay. It is interesting, but it is useless. 3 millikelvin data is useless. Okay. Pardon? Thermal effects will affect. Yes, yes, we are going to learn that later. Okay, let us do the first question. So, the first question is okay. I think sorry. Okay. Anyway, you scan using this one. Okay, let us go to question 1. So, question 1 is about how many layers are required in the case of an in-plane MRAM with an aspect ratio of 1. So, when you say aspect ratio, basically it is the length divided by length width ratio. Okay. So, aspect ratio 1 is basically like the length and width are same. Okay, many of you are wrong. Okay, MTJ requires how many layers? MTJ requires 3 layers, right? So, you need a reference layer, you need a magnesium oxide, you need a free layer. Okay. But we just learnt that if you are doing in plane MRAM, your magnetization can be at any angle within the plane. So, we need to define an easy direction. So, for that we need an AFM layer and the recipe that we need to pin the magnetization along certain direction. Okay. So, the correct answer is 4, not 3 or 2. I do not know who answered 3, 2. Okay. You really need to brush up whatever we have been learning so far. Okay. Okay, correct answer is 4. Okay, next question. Okay, I am giving you some more time to give you, to give you time to answer correctly. Okay, many of you are wrong, like 14 of you are wrong. Okay, the correct answer is both. You should have chosen both. So, some of you have chosen both, I think. So, we are using an antiferromagnetic layer not just to fix the pin the magnetization direction, we are also using this to set the desired EZ axis. Okay, otherwise the magnetization is in random direction. Okay, majority of you are right. I mean, there is nothing stops us from using shape of the MRAM cells physics wise, but if you use shape, you have to use ellipse, which occupies more area than a circle for a given diameter. Okay, so the correct answer is this one. Okay, so far we learned that we need at least 4 layers. So, antiferromagnetic layer, free layer, magnesium oxide reference layer. Okay, but we learned that if you have a reference layer like this, let us say this is your reference layer and this is your free layer. Let us say you magnetize the reference layer along certain direction. So, this is like north pole, south pole. So, you know that this will generate a magnetic field. Okay, so, this magnetic field can interfere with the free layer magnetization. Okay. So, if this is north pole, the free layer having this kind of magnetization is preferred than free layer having magnetization in this direction. Okay. So, anti-parallel direction is preferred than parallel direction. Okay. This we do not want. So, we do not want this free layer direction to be parallel or anti-parallel, not by this magnetic field. This should be decided by us. Okay. Suppose we want 1, we keep the magnetization to be anti-parallel. Suppose we want 0, we keep the magnetization to be parallel. Okay. We don't want this magnetic field to influence the magnetization direction of the free layer. Okay. So, to overcome that problem, people use the synthetic antiferromagnetic concept. Okay. So, 2 days ago I discussed this concept. So, if you have 2 ferromagnetic layers separated by a suitable thickness of ruthenium layer, so we learnt that the neighboring magnetization can point in anti-parallel direction. So, this is the synthetic antiferromagnetic concept that we learnt a few days ago. Okay. So, when we have that synthetic antiferromagnetism set here with a ruthenium layer or iridium layer, now these 2 layers are anti-parallel in direction, and you can notice that this is like north, south. Okay. So, this is stable. The magnetization, I mean the magnetic field from this layer will go into this layer, the magnetic field from this side will go here. Okay. So, none of this field will go to the free layer. Now, you can notice that after we use the synthetic antiferromagnetic layer design, the stray field from the reference layer does not go to the free layer. Okay. So, it is just stuck within the reference layer itself. Okay. Now, free layer is free from stray magnetic field. Okay. So, for that reason the in plane MRAMs usually have this SAF design. Okay. So, now if you count the number of layers, so we have 1, 2, 3, 4, 5, 6 layers. So, previously we had like only 4 layers. I mean a simple MTJ has 3 layers. Okay. When you introduce pinning, we have 4 layers. When you introduce synthetic antiferromagnetic layers, now you have 6 layers. Okay. So, this is how the technology progresses. Okay. Then the second concept that we need to learn about the in plane MRAM is the thermal stability. Okay. So, a few days ago I taught you this thermal stability concept. So, we learnt that KUV is the anisotropy that stabilizes the magnetization. So, that is the energy required for storing information, and if you make the volume of the entity that stores magnetization to be small, your KUV will be small, then the magnetization will not be stable. So, we learnt that the magnetization of the smaller units may flip as a function of time. This is not a video, I think, it is just a screenshot. So, in the video you notice that this magnetization was flipping as a function of time. So, it was pointing left, sometime pointing right, sometime, and so on. Okay. So, this phenomenon happen in the magnetic recording. So, for in plane MRAM, usually we are using cobalt iron boron, which has a low anisotropy constant. So, the Ku itself is small. Okay. So, the volume cannot be much smaller. Okay. So, there is a limit to the volume. So, in the case of cobalt iron boron for in plane MRAM design, the diameter cannot be smaller than 60 nanometer. Okay. So, if you make the MRAM diameter smaller than 60 nanometer, your KUV becomes smaller, then KBT competes, then your magnetization starts fluctuating. Okay, you can do some calculation. For example, this is the anisotropy constant of cobalt iron boron. So, you know the Ku. Let us say you make 5 nanometer thick cobalt iron boron. You can calculate the diameter for this ratio. Okay. So, you want the KUV by KBT to be more than 60. So, this gives you 10 years of stability. Okay. So, once you write information, the information will be stable for 10 years if this ratio is more than 60. Okay. So, knowing the anisotropy constant thickness, we can calculate what will be the diameter of the MRAM cell. Okay. So, if you substitute all these things, you will get the diameter to be 60 nanometer. Okay. So, what it means is that if you use cobalt iron boron with in plane magnetization for storing MRAM, you cannot achieve MRAMs below this diameter. So, this is the limit for in plane MRAM. So, that is one problem. Okay. So, problem of in plane MRAM, one problem is thermal stability. It limits to 60 nanometer. Okay, the second problem with the in plane MRAM is the writability. Okay. So, we know that magnetization is the angular momentum, spin is the angular momentum. So, let us say you have a spinning top. Okay. Spinning top is rotating like this. Okay. So, spinning top is rotating like this. So, its angular momentum is along this direction. Okay. So, when the spinning top is very fast, rapidly rotating, the angular momentum of the spinning top will be along this direction. But you would have noticed when the spinning top slows down, then this angular momentum is not in the perpendicular direction, it is like this. Okay. So, at some point of time when it slows down, the spinning top will go like this, then fall down, right. So, you would have noticed when you play with the spinning top, what is the word for spinning top in Hindi? Huh? Lettu. Okay. Okay. So, spinning top does same thing, right, like angular momentum is not coming down from this to this directly. So, it is like this, then slowly precesses, finally, the spinning top falls down. Okay. So, similar thing happens when you switch magnetization. Magnetization is an angular momentum. So, like the spinning top's angular momentum, magnetization also has angular momentum. So, if magnetization is pointing in this direction, so if you want to make magnetization to be in the opposite direction, again it has to be like precess, then finally switch to the other direction. Okay. So, this is the typical switching behavior. I mean, you cannot see this in VSM, in vibrating sample magnetometer or anything, you are measuring at a time scale of say few seconds. Okay. So, this precision, all these things happen in picoseconds, okay, hundreds of picoseconds. So, the magnetization goes from one direction to the other via precision. Okay. Now, let us take in plane MRAM. Let us say this is the initial magnetization direction. This is the final magnetization direction. So, during the switching, you see the path of magnetization. So, at one point of time magnetization is like this, then precesses at some point of time it is precessing like this. Okay. So, this direction is perpendicular to the easy direction. Okay. So, you see that the magnetization direction is perpendicular to the initial direction. Okay. So, this point I should teach you something which I did not teach you before. Okay, let us spend some time to learn some concepts before we come back here. So, let us go back to the Stoner-Wohlfarth switching, all those things. Let us say I have a piece of magnetic material, it has an easy direction and a hard direction. So, which of these two curves, okay, these are MH curves, right. So, which of these two curves is along easy direction, which is along the hard direction? Red is which direction? Red is along the easy direction and green is on hard direction, right. And what is this field? No, what was the term I used when I taught you the Stoner-Wohlfarth reversal mechanism? HK. Okay. So, we learnt that if you have a Stoner-Wohlfarth particle which has certain anisotropy direction, the easy and hard direction hysteresis loops will meet at this field called anisotropy field. Okay. So, this is something that we learnt, but there is something which I did not teach you before. Let us say we have a thin film, there is no other anisotropy, okay, no special anisotropy, I mean no other form of anisotropy. And this is a thin film. Okay, so, what makes the magnetization to be lying parallel to the film surface? Shape anisotropy, right. So, shape anisotropy will make the magnetization to be parallel to the in plane direction. Suppose I apply a magnetic field along this direction in the perpendicular direction. How much magnetic field that I need to make this magnetization to rotate in the perpendicular direction? Okay, initially the magnetization is parallel to this plane, but I apply magnetic field in the perpendicular direction. So, at some field it will come in the perpendicular direction. So, what is that field? I did not teach you, so you may not know, but you can guess. Okay. I did not teach you, so it is okay. So, the field you require to make this magnetization come out of this plane does not depend on any of these things. Okay. So, it is nothing to do with HK, all those things, because we say that there is no special anisotropy except shape anisotropy. Okay. So, in this case the field you require to make the magnetization to be perpendicular is 4 pi m s. Okay. So, it does not depend on anything else like HK, all those things. So, this is only when we are talking about Stoner-Wohlforth mechanism, but in the absence of any other anisotropy, the field you require to make the magnetization perpendicular to the plane is only given by this formula. Okay. It is just proportional to m s. Okay. So, if your saturation magnetization is larger, then you need more magnetic field. If your saturation magnetization is smaller, you will need less magnetic field. So, for example, you take permalloy with a magnetization of 800 EMU per cc. Okay, permalloy will have magnetization in the plane, and if you want to make the permalloy loop in the perpendicular direction. So, in the perpendicular direction, permalloy loop will saturate at this field, which is 4 pi times 800 EMU per cc. So, that will be roughly around 10,000 postal. So, if you take say cobalt iron with a ms of 1200, so it will saturate at around 15,000 Oersted. Okay. So, this saturating field in the absence of any anisotropy depends only on this 4 pi ms. Okay. So, with this let us go to the next slide. But we can say that perpendicular direction is the hard axis. Yes, perpendicular direction is the hard direction. Yes. So, in this case it is the shape anisotropy that makes the magnetization in plane. This is not the same as HK. I mean, we do not use the word HK here. Okay, so, with that learning what we learned, let us come back here. So, you know that the magnetization is comfortable either pointing left or right or even in any direction within the plane, because the shape anisotropy makes the magnetization parallel to the film plane. But if you want to make the magnetization perpendicular to the plane, you have to spend a magnetic field. I mean, you have to apply a magnetic field of the order of 4 pi m s, right. This is a huge energy. Okay. So, if you convert this magnetic field into energy, it will be a huge number. Okay. So, when you switch magnetization from right to left, what you are doing? So, quite often the magnetization is perpendicular to the plane. Okay. So, all this region you are spending more energy, more than the anisotropy energy that keeps the magnetization stable. Okay. So, that is what I have written here. So, the energy barrier that retains the information is 60 times kBt, but when you do the reversal process, the magnetization spends long time in the hard direction. Okay. So, the energy required to reverse the magnetization is like 6000 kBt. Okay. So, it is more 100 times more than the energy that keeps the magnetization stable. Okay. So, this is a problem. So, when you want to write in plane MRAM, you are spending too much energy, the energy much more than the energy barrier to write information. So, this is the second problem. So, first problem is thermal stability, which limits the diameter to be more than 60 nanometer. The second problem with the in plane MRAM is that you spend too much energy to write bits. Okay. So, we spend too much energy in writing information. So, there are some formula, but you do not need to worry about this formula. So, but you will notice that all this formula includes the 4 pi m that I described before. So, this H p also is same for pi m s. So, if you look at many papers related to MRAM, you will find either the critical current required to write information or some voltage required to write information, and in all of them you will find this term 4 pi m s. Okay. So, you need to spend more energy to write information. Okay. So, let us do some question and we can take a break. Okay, majority of you are wrong. Okay. You are wrong because you thought this is the right answer. This is not right answer. We are using an antiferromagnetic materials. We are using an antiferromagnetic material like iridium manganese to pin the magnetization direction. Okay, but sorry. So, synthetic antiferromagnetic structure does not pin the magnetization direction. Okay. So, what synthetic synthetic antiferromagnetism does is it makes the two layers to be anti-parallel. Okay. So, synthetic antiferromagnetism only makes the two layer magnetization to be anti-parallel. So, the two magnetization can be like this or like this. So, it can be in any direction. It does not pin in any particular direction. Pinning happens only with antiferromagnetic materials. Okay. So, we are using this only for reducing the stray magnetic field. So, 2 is the correct answer, only 4 of you are right. So, synthetic antiferromagnetism is different from the antiferromagnetism and exchange bias concept that we learned. Okay. So, be clear. So, this kind of question helps me to understand whether you are following correctly or not. So, we can recalibrate our knowledge by going through such question. Okay. So, antiferromagnetism is helping us to pin the magnetization direction. So, this is the one that helps. Okay. So, I hope you remember we are using antiferromagnetic material to pin the magnetization along particular direction. So, these materials are iridium, manganese, iron, manganese and things like that. Okay. So, when we are talking about synthetic antiferromagnetism, we are talking about two ferromagnetic layers like cobalt and boron separated by some material like ruthenium, iridium and things like that. So, this is synthetic antiferromagnetism. So, this is a material, is a natural material, this is a synthesized material. Okay. So, you should know the difference. Secondly, this synthetic antiferromagnetism only ensures that the magnetization is antiparallel. Okay. So, if I view from top, let us say we have several magnetic units which are in synthetic antiferromagnetic shape. So, from top they may be in any direction. Okay. So, if the top magnetization is pointing in one particular direction, the bottom will be antiparallel to that. Okay. So, what synthetic antiferromagnetism does is only this. Okay. It will make the top and bottom to be antiparallel to each other, but it cannot help in pinning this magnetization to be any particular direction. Okay. So, for pinning you need this concept and the magnetic field annealing. Okay, next question. Okay, again majority of you are wrong. Okay. I do not know, is it tough to follow? Okay, the energy barrier of in plane MRAM. I told you that we designed the energy barrier to be roughly 60 kBT. So, the KUV is roughly 60 kBT, but I told you that when we try to write information, the magnetization is going through precision, and the precision, there is a lot of time spent with magnetization in the perpendicular direction, and because of that I told you that the energy we require for writing information in the in plane MRAM technology is 6000 kBT. Okay, so, this is the energy barrier, and when you talk about this energy required to write information, it becomes larger than the energy barrier height because of the 4 pi ms term here, okay, because the magnetization is like processing the direction, the hard direction, right. So, it is this one that causes the writability problem. Okay. So, if ms is large, this energy will be even larger. If ms is small, this energy may be a bit large, a bit small. So, it is basically the saturation magnetization that causes the writability problem. Okay, so, the YouTube streaming videos are available. So, maybe after you go home at night, you can watch the videos again to reinforce the concepts. Okay. So, the next one is the perpendicular MRAM. So, we will cover this after a break. Okay, we will go for tea now. Tea is ready, right? Okay, there is an announcement. Yes, please wait. Yes. You want to use mic?
So we have distributed this offline form, right, feedback form. So now we are going to upload one Google form where we have to upload these documents and all. For offline, we will be floating on Google Form. So there you have to upload your document like the Aadhaar card, PAN card, whatever, with the ID number and other details, whatever it's mentioned, okay, in the Google Form. Along with that, you have to scan this offline feedback form and you have to upload that also. So it should be a mandatory section in the Google Form itself. First thing. And second thing, once the scanning is done, keep your documents and you submit this offline form to the volume again. Okay, you submit it back. So we need offline and online both feedback forms. Okay. So just fill the feedback forms, scan it, keep with you, and submit back. Okay. Yeah, that is it for the offline. So you can leave. Okay. And one more thing, the deadline for the form will be today, 4 p.m. So we are floating it right now. So try to fill it. Okay. In between the breaks, or it will not take more than 10 minutes for everyone. Okay. So try to fill it by this. On kar. ऑनलाइन को म्यूट कर म्यूट कर Okay, for online participants, we'll share one PDF file to you, and that is a feedback form. So you have to print it, you have to fill it, and we need your signature there, and then you rescan it and submit in the Teams group. There is a folder I have just created with the name feedback form. So you all have to upload the feedback form there. Okay, yeah, that is for the online. So please print it, sign it, and fill it. Then you just upload it again. Okay, rescan it.
So, we will come back by 11:35. So, today we need to finish before 1. So, it's not going to the 3 layer, right?
No, but if we don't have it.
If you don't have, then so where is your reference layer? Yeah, the reference layer is in the form of layer.
It's
So we need a
but it's not
reference layer.
pinning.
Pinning is done by
It's a different
the
layer.
ferromagnetic layer at the bottom, the antiferromagnetic layer at the bottom. Okay, maybe I will explain it.
Yeah, just one.
Yeah. Yes. Yeah. Declare this whole essay. Yeah. Yeah. Yeah, so in the essay, let's say the spinning layer spinning this direction. So this spinning. Yeah, so I mean fixed layer now when you read information, right, it is this two angles will decide the reading. This won't come into picture because reading is the interface related.
Absolutely.
টিউটোরিয়াল কি আজকে লাস্ট হবে না এরপর হবে? আজকের দিন হবে। আজকের দিন যে হবে তাহলে সে কী করবো? আমাদের তো যেটা শেষ হচ্ছে ঠিক আছে, এখন স্টাডি করা ছিল ওইটা কাইন্ড অফ সিমিলার থিংস, তো ওইটা করোনা বুঝতে পারছি। ফার্স্ট ক্লাস শুটিং দেখা
Okay, it looks like there is some difficulty in understanding when I introduce synthetic antiferromagnetism. So let me explain again. So your normal in-plane MRAM as a free layer, magnesium oxide, a reference layer, which is pinned along certain direction by antiferromagnetic layer. Okay, so this is the normal in plane MTJ. Okay, so when I introduce synthetic antiferromagnetism, you are getting confused. Okay, so synthetic antiferromagnetism based MRAM also has everything similar. So we have a free layer, you have magnesium oxide, okay, you have a reference layer, then you have a AFM layer. Okay, the only difference between the SAF structure and the normal in-plane MTJ is that this reference layer doesn't have one layer. So here we have only one reference layer. Okay, so in the case of synthetic antiferromagnetism concept, this reference layer is made of 3 layers. Okay, so the bottom layer of the synthetic antiferromagnetic structure is pinned by the AFM, so it will be along this direction. Then you have ruthenium or iridium to induce the antiferromagnetic coupling. Okay, so instead of one layer, you have 3 layers. Okay, so your reference layer is like this. This whole thing is the reference layer. So when you read information, what matters is the top ferromagnetic layer. Okay. Okay, so your top magnetization of the reference layer is along this direction. So if free layer is parallel to that, you will have low resistance. If your free layer is anti-parallel to the top layer magnetization, you will have high resistance. Okay. So when you are talking about reading, we are talking about, let's say this is the magnesium oxide, this is free layer. So we are only talking about this layer.
Why do we need to close the stray fields? That's why we are using SAFs.
Yeah, why do we need to close the stray field? Is because otherwise, you know that this is the like north pole of a magnet, south pole of a magnet, right? This field is coming and influencing the free layer magnetization. Okay. So if there is a magnetic field, so this direction will be favored, okay, whereas free layer magnetization in the other direction. This is not favored. Okay, this is like having 2 north poles parallel to each other.
Then also, yeah, you took H equals to 4 pi ms
Mm.
for thin films.
Mm-hmm.
So, I mean, what what constitutes a thin film? I mean, how far you can stretch this formula for bulk materials?
For bulk material, let us say you have a, okay, this is coming from the shape anisotropy. So, you look at the concept that we learnt about demagnetizing field in the magnetism chapter. So, when I introduce the stray field, I mean sorry, not stray field, shape anisotropy. So, when I introduce shape anisotropy, I mentioned that the demagnetizing field is responsible for this shape anisotropy, and this is basically a tensor. So, depending on the shape of your object, you have a demagnetizing field tensor. So, if your bulk magnet is in spherical shape, this demagnetizing tensor has equal value in all direction, because spherical is uniform, right. So, if you have a flat object like this, the demagnetizing field is stronger in this direction. Okay, so now let us move on to the next topic, which is about perpendicular MRAM. So, as the name implies, let us say this is your wafer, the magnetization will be perpendicular to the wafer plane. So, that is perpendicular MRAM. So, let us say you have a reference layer pointing in the up direction, your free layer can be parallel or anti-parallel, that gives rise to state 0 and 1. Okay. So, only when we are talking about in plane MRAM, so within the plane magnetization can be in any direction, but out of the plane magnetization is like only either up or down, right. So, you do not need a pinning layer in the case of perpendicular MRAM, you do not need a pinning layer, you just make this layer to have a very large coercivity. You can have the free layer to have small coercivity. Okay. So, whether you apply magnetic field or spin transfer torque, that current will be only switching the magnetization of this free layer to be parallel or anti-parallel. It will not affect the magnetization of the reference layer, because it has a large coercivity. So, you do not need the antiferromagnetic materials to pin the magnetization direction. So, this is like the concept pseudo spin valve that we learnt. So, we just make use of some large coercivity material here, so that during the writing operation you only switch the free layer magnetization. Okay. So, in this case, I mean if you make a thin film, in the absence of anisotropy, magnetization will lie in plane, but if you have certain material with sufficient anisotropy, then you can point the magnetization to be out of plane. So, usually the perpendicular MRAM uses materials with a larger anisotropy. So, this anisotropy is needed to make the magnetization point in the perpendicular direction. Okay. So, we mentioned that in the case of in plane MRAM, we spend extra energy to write information, but here we do not have that problem. Okay. So, here we have an anisotropy which can lift the magnetization from in plane to the outer plane direction, right. So, if you want to switch, I mean if you want to keep the magnetization in plane. So, if you remember the Stoner-Wohlforth case, this is easy direction, and this is the hard direction loop, right. So, here we have certain anisotropy in the perpendicular direction. So, perpendicular direction is the easy direction and in plane direction is the hard direction. Okay, so, if you want to make the magnetization to be lying parallel to the MRAM, the parallel to the wafer, you are just applying a field that is equivalent to Hk. Okay, you apply a magnetic field equivalent to Hk, then you can tilt the magnetization in the hard direction. Okay, so, because of this reason, in the case of perpendicular MRAM, the writing energy and the storing energy are same. Okay, so, we have learnt that the energy barrier is coming from anisotropy, right, KUV. Which in other words it will have this formula. Okay, so, you do not spend extra energy in writing operation. So, we can say that writability in perpendicular MRAM technology does not need extra energy to write information. So, that is the first advantage. The second advantage is the thermal stability. So, for in plane MRAM we said the minimum diameter is around 60 nanometer, right. We cannot shrink the MRAM to be smaller than 60 nanometer, but perpendicular, I mean materials with a perpendicular anisotropy, they have very large anisotropy values. For example, you take iron platinum, it has a value of 7 times 10 power 7 per cubic centimeter. So, if you take a cube of or small diameter of iron platinum, so for diameter as small as 2.6 nanometer, you can make the magnetization of this iron platinum to be thermally stable. Okay, so, in this particular case I do not remember what is the thickness, okay, but you can calculate what can be the, let us say if your thickness is 2 nanometer, what will be the diameter of iron platinum that can retain the information for 10 years. You can calculate based on the formula KUV by KBT to be 60. Okay. So, KU you take from here, okay, this value is the KU. So, you know the thickness, you want to calculate diameter. So, the volume is somewhere here. Okay. So, you can calculate the diameter based on these numbers. Okay. But right now I am saying is around 2.6, but for very thin films this may be slightly larger. Okay. So, there are many materials like this with a very large anisotropy. So, you can use these materials for making perpendicular MRAM. Okay. So, with this idea people have started looking at perpendicular MRAM for many years. Okay. So, if you look at this paper, for example, this paper was published in 2002. So, in this paper these researchers have used terbium iron cobalt as a layer that can retain the magnetization in the perpendicular direction. Okay. So, this terbium iron cobalt is a material, is an amorphous material. So, people have been studying this material for many years, like almost 40, 50 years, for application in something called magneto-optic recording. Okay. So, this recording technology was popular around 1990 to somewhere 2000, something like this. So, when I was doing postdoc, I used to carry this for playing songs. Okay. So, those days we do not have like smartphone. So, we need to carry some device to play music. Okay. So, this is a music player where we insert this disc. So, this disc can store songs lasting 74 minutes. Okay. So, this disc is called a magneto-optic disc. So, I mean this is a magneto-optic disc for storing information like computer data. So, I used to back up my information in this disc, and this is called a mini disc. So, we can write songs into this disc and play music. Okay. So, this is called magneto-optic recording technology. Okay. So, this technology uses this material, and this material can give rise to perpendicular anisotropy. So, that means, if you grow this terbium iron cobalt on certain substrate, the magnetization will be pointing perpendicular to the disc surface. Okay. So, these researchers from Japan, they proposed that we can use them for perpendicular MRAM. Okay. So, if you look at this structure, you will see an aluminum oxide. Aluminum oxide is the barrier for tunneling. Then we have free layer, this is the free layer. And one of them is a reference layer. Okay. So, you can magnetize this free layer to be parallel or anti-parallel and store bits 0 and 1. Okay. So, this is one of the earliest proposals of perpendicular MRAM. Okay, but there are a few problems with this particular technology. First problem is corrosion. Okay, these are, I mean, materials like terbium, erbium, all these materials can easily corrode. Okay. So, if you buy a terbium target and keep it in your desk for a few days, you will see that it has become black. Okay. So, they can oxidize easily. So, this is one of the problem. First problem is that they cannot withstand corrosion. The second problem with this particular technology is like you need to use very thick layers like 30 nanometer terbium iron cobalt, 50 nanometer gadolinium iron cobalt and things like that. So, only then you can get PMA. So, later you will have writing problem when you have very thick layers. The third problem associated with this material structure is the damping constant. Okay. I haven't explained what is damping constant so far. So, next slide I will explain what is damping constant. So, I told you that magnetization is the angular momentum. So, if you switch the magnetization from one direction to the other direction, it precesses, then finally goes to the other side. So, you notice that initially it was in this direction, then when it comes to this direction, it does not quickly settle into this position. Okay. So, even after it has reached the other direction, it keeps precessing, then finally slowly settling into one particular direction. So, you see there are so many precession happening. So, for example, I used to carry a ruler. So, if you have something, you I mean if you have a ruler, right, the scale, if you like give a force, then the ruler will vibrate, after some time it will settle, right. So, the settling is basically because of the damping of oscillation. So, if you have some oscillations and how fast you damp, that is related to the damping constant that we are discussing. Okay. So, there are two possibilities. In one possibility it takes very long time. So, it goes through so many precession, then finally stops here. So, this means low damping. Another possibility is like it comes here, then quickly stops. Okay. So, this is like high damping. So, if the magnetization settles faster, that means high damping. If the magnetization settles slowly, we have low damping. Okay. So, which is better, high damping or low damping? High damping. Okay. Anyone says low damping? Okay, depending on what you are looking at. Okay. So, if you are looking at the speed of operation, okay, if you are looking at the speed of operation, high damping is better, because your magnetization was initially in this direction, you apply say spin transfer torque or magnetic field. So, this is precessing fast and comes here settle fast. Okay. So, that means we can switch from one direction to the other direction fast. So, high damping is good for speed. Okay. So, that is what I have written here. High damping is useful for faster reversal. On the other hand, if your damping is high, so what does damping means is the ability to disturb from the initial position. Let us say, okay, let me go back to what we learnt yesterday. So, when we learnt about spin transfer torque yesterday, let me break this slide. So, if you remember the learning yesterday, when we talked about spin transfer torque, I was talking about magnetization making certain angle with respect to the applied field. Okay. So, magnetization precesses around the field. Okay. This is something that we learned. Then I also told you that there is some Gilbert damping, which forces the magnetization to be parallel to the field. Okay. So, damping helps to make the magnetization parallel to the applied field. We can say quickly, I mean in another aspect we can say that if your damping is high, you need more energy to make the magnetization precise, okay, or even switch information. Okay. So, that is the second point. So, if your damping is high, you need more current or more field to switch the magnetization. Okay. So, there are benefits as well as problems. Okay. Damping helps to improve speed, but damping makes the writing current larger. So, if you look at the materials that we just discussed, these materials had a high damping constant, which means we need more current to switch this magnetization. Okay. So, that is another problem. So, they need more energy for writing. Okay, so, after this study, not many people studied this material. Then people also started looking at cobalt, palladium, cobalt, platinum multilayers for MRAM applications. So, here the interface anisotropy is the one that makes the magnetization perpendicular, and this research was carried out say around 2010. So, here again the damping constant is large. So, you need more writing current, that is one problem. The second problem is that these materials grow with FCC 111 texture, which is not good for magnesium oxide 002. Okay. So, tomorrow you will learn that this kind of texture is good for achieving high TMR. So, if the materials you grow for MRAM disturb this crystalline formation, then your TMR will be sacrificed. Okay. So, this is second problem. So, you notice that in all these cobalt palladium multilayers, TMR ratio is very low, around 20 to 70, whereas we are able to get around 200% TMR in current products. Okay. So, comparatively you notice that these TMR values are not good. That is because the crystal structure are different. Okay. However, these materials have very large anisotropy field and they are suitable for reference layer. So, you cannot use this material for free layer, but you can use this material for reference layer. So, towards the end of the day I will tell you that these materials are used as the reference layer in perpendicular MRAM. So, this is also not very useful as a free layer material. Okay. We cannot use cobalt palladium materials for free layer, okay, not useful. Then people also looked at iron platinum based MTJs. So, I told you that iron platinum has a very large anisotropy constant. So, they can support small MRAM sizes about 5 nanometer. So, earlier I told you 2.5, that is for a cube I think, but if you make thin films of iron platinum, you can achieve 5 nanometer size using iron platinum MRAM, and the crystal structure of iron platinum also supports the MGO 001, which we discussed earlier. So, this also no problem, but again these materials have very large damping constant and you need a very large writing current to write information. Okay. So, writing power is a problem with these MRAM. So, you see people did not like sit idle, they tried so many materials with perpendicular anisotropy to achieve perpendicular MRAM, but until this point somewhere in 2010 nothing worked. So, all the materials people looked at had some problem or the other. Okay. So, I already told you if alpha is larger you need a very large writing current. So, most of the material that we saw earlier all had very large damping constant. So, this is the damping constant. Okay. So, because of the writing current, larger writing current, they were not useful. Okay. So, you look at all the material that I showed you before, cobalt platinum, cobalt palladium multilayer, all this iron platinum, all this material have very large anisotropy, which is good. I mean, large anisotropy is good, because you can make smaller MRAM, but all these large anisotropy material also have large damping constant, which is not good. Okay. So, you want to have large anisotropy, but small damping constant. So, somewhere here in this circle. So, until 2010 we did not have any material with a large anisotropy, but small damping constant. Okay. But a breakthrough happened in 2010. So, a group from Tohoku University in Japan, the group led by Professor Ono. So, they came up with a material which had the desired characteristics. So, I told we are looking at some materials which have large anisotropy constant, but low damping. So, I told you we are looking at materials in this area. So, the materials proposed by this group in Tohoku by Professor Ono and other people. So, they had these properties. Okay. So, before I tell you what it is, let us do some questions. Okay. Okay, both are correct answers. Perpendicular MRAM materials have high anisotropy constant, so you can make them smaller. Smaller MRAMs are possible with perpendicular MRAM, and they have better writability compared to the in plane, because you are not spending extra energy more than the storage energy. Okay. Next question. Okay, most of you are right. This terbium and cobalt has a high damping constant and it has a corrosion problem. So, all of the above is the correct answer. Okay, so cobalt palladium multilayers grow in FCC texture, which is not good for MgO BCC. So, they have this poorer TMR problem. They also have large damping constant. So, both has to be pressed. I think most of you have done that. Okay. So, most of you are right. Okay, here many of you are wrong. Okay, I told you that the iron platinum has a very good lattice matching with respect to magnesium oxide. So, the TMR is not affected, only problem is the higher damping constant. So, this is the correct answer, not both. Okay, let's skip this one. Okay, so I told you that all the materials that we had studied before had very large anisotropy constant, but they also had large damping constant, and we were looking for materials with a lower damping constant and large anisotropy field. So, in 2010 the group of Professor Ono from Tohoku University, they came up with this material like tantalum, cobalt iron boron, magnesium oxide, which had a perpendicular anisotropy, which had reasonably high values of anisotropy constant and a lower damping constant than any other PMA material that we had. So, from here now we have come to this region. So, lower values of damping constant, but reasonably high values of anisotropy constant. They were achieved in this tantalum, cobalt iron boron, magnesium oxide system. Okay. So, we can say that this is a boon for the first few generations of STT MRAM. Okay. So, once this material was published, there were a lot of interest. Okay. So, we know that let us say we have some layer like tantalum, and on top of this we grow cobalt and boron. Let us say if this layer is quite thick, say 3 nanometer or something like that. Okay. So, we know that magnetic films will have easy access in the in plane direction. Okay. So, quite for many years people were studying cobalt iron boron based in plane MRAM. So, if you remember a few slides ago I was showing cobalt iron boron, magnesium oxide, cobalt iron boron, things like that. Okay. So, this is not a new material. Okay. Cobalt iron boron, magnesium oxide, cobalt iron boron, these are not very new materials. People were using 3 nanometer or 5 nanometer of cobalt iron boron, okay, and the magnetization was lying in plane. So, they were using this as a in plane MRAM material. Okay. So, what this group did was shrink this thickness from 3 nanometer to 1 nanometer. Okay. So, they were curious, what if we do not make this cobalt and boron very thick, but make them thin. So, whether we can get some kind of interface anisotropy like we get in cobalt platinum multilayers, right. So, they wanted to see whether we can get some form of interface anisotropy by making this cobalt and boron very thin. Okay. So, that is what they were working on, and that the Tohoku University group and another group from IBM, they worked on this concept almost at the same time. And here I am showing the results from IBM group. Okay. So, here you notice this is cobalt and boron thickness. So, this cobalt and boron was deposited either on tantalum seed, blue is the tantalum seed, that means on top of tantalum layer they are growing the cobalt and boron magnesium oxide, and this red color is on top of ruthenium. Okay, so, ruthenium, okay, I also have to explain what does this mean. So, when you say Ku, so positive Ku means the magnetization is perpendicular to the disk surface, I mean wafer surface. When we talk about negative Ku, it means magnetization is in the plane. Okay. So, that is what is shown here. So, here you see is positive. So, above this line Ku is positive, which means magnetization is perpendicular. Below this line Ku is negative, which means magnetization is in plane. Okay, so, this is the cutoff line. So, when you grow cobalt and boron on top of ruthenium, Ku is always negative. So, even if you make the cobalt and boron thinner, Ku is always negative, which means magnetization is lying in plane. Okay, on the other hand, let us say we grow cobalt and boron on top of tantalum shown by the blue dots, Ku is negative until this point, which means magnetization is in plane, and when you go to about 1 nanometer, you see the Ku becomes positive. So, in this region you can see Ku is positive, which means for this range of thickness magnetization can lie perpendicular to the disk surface. Okay, so, this is the observation from IBM, and the group of Tohoku also have similar observation, which I will explain using this graphs. Okay, let me zoom in the graphs. Okay, these are too small. Let me get this one. Okay, for you this task may be easy, but I am spending more time. There is a reason, I will explain later. Okay. Okay, now we look at the results from Tohoku University. So, here they plot the hysteresis loop of the sample with the cobalt and boron thickness of 1.3 nanometer and 2 nanometer. Okay, so, red means the magnetization is, I mean let us say this is your sample. They apply magnetic field either in the perpendicular direction or apply magnetic field in the plane direction, and they measure two hysteresis loops. Okay. Blue is actually this one. Let me use the color code, correct color code. Blue means magnetization is applied in the parallel direction. Okay, so, when magnetization, I mean the thickness is 2 nanometer, this is the easy direction, right. So, easy direction has larger remnants, it saturates quickly. So, easy direction is in plane and the other direction is hard. On the other hand, when they reduce the thickness of cobalt and boron to 1.3 nanometer, you notice that the perpendicular direction is the easy direction, because it saturates quickly and it has larger remnants. So, we learned this before. Easy direction, we have larger remnants, we can saturate quickly, and the blue direction is the hard direction. So, perpendicular direction is the easy direction and in plane direction is the hard direction. Okay. So, that means, if you make tantalum, cobalt, iron, boron, magnesium oxide, and if this layer is very thin, for example, around 1 nanometer, then the magnetization of this layer is going to be perpendicular. Okay. For the same structure, if you make a tantalum, cobalt and boron, magnesium oxide, and if this layer is like 2 nanometer for example, it is going to be in plane. Okay. So, just by changing the thickness of this layer, they have produced some interface anisotropy, okay, which leads to the perpendicular anisotropy. Okay. So, the beauty of this material is that its damping constant is very similar to the cobalt iron boron, which we use for in plane application. So, damping constant wise no big difference. Okay. So, but it can have very large anisotropy. So, it can make the magnetization perpendicular. Okay. So, there is some reason why the interface anisotropy is observed. So, people say that it is due to the hybridization. Let us not go into the details. Let us come back to the results of Tohoku University. So, here they study many different properties, like what is the anisotropy field. So, you have learnt that anisotropy field is the 2 Ku over ms. So, anisotropy field, then damping constant and the tunneling magnetoresistance, all these property they study as a function of thickness of the cobalt and boron. Okay. So, when the thickness is very large, say 2 nanometer or above, this value is small, negative, but when you go towards smaller thickness, you see large anisotropy field, positive anisotropy field, which makes the magnetization perpendicular. Here is in plane. And you will notice that when you reduce the cobalt iron boron thickness, alpha increases. Okay. It looks very large here, but still this alpha is much lower than the damping constant of 0.1 that we saw in other materials before. Okay. So, we saw so many other perpendicular magnetic material which had alpha of 0.1, but this material still has a lower damping constant, which means you do not spend too much energy to write information on this material. Okay. And this material also supports high TMR ratio. So, in this graph you will see that this material does not spoil the TMR ratio, is still as high as 100%. This was okay. Okay. But now people have made this to be like even 200%. So, all these results indicate the potential use of this material. So, anisotropy is high, damping constant is not a problem, all those things. Okay. And this group showed that you can make MRAM as small as 40 nanometer. So, this number is 40 nanometer, and you can achieve MRAM property. So, from this study they showed that in plane MRAM can be only shrink to 60 nanometer, but if you use this material tantalum, cobalt iron boron, magnesium oxide, you can bring this down to around 40 nanometer. Okay, so, after this paper was published in 2010, many companies started making MRAM, and now it's a product. Okay. Okay, let's do some questions. So, this kind of PMA that I have described so far is called interface PMA, okay, IPMA. We use this term IPMA for this particular form of perpendicular magnetic anisotropy. Okay, so this particular thing is scalable to 35 nanometer, and it is also easier to manufacture. Okay. So, the correct answer is all of the above. Okay, next question. The interface PMA depends on okay, so I did not teach you this clearly. So, wrong answers are okay. The correct answer is all of the above. Okay. So, if you remember the discussion we had, I showed you two data from IBM. In one case they used tantalum below cobalt iron boron, in another case they used ruthenium below the cobalt iron boron. So, in the case of ruthenium there was no perpendicular magnetic anisotropy, only the tantalum seed layer gave rise to the perpendicular magnetic anisotropy. Okay, so, seed layer plays an important role. Of course, you all know that the thickness of cobalt iron boron layer plays an important role. I did not teach you that this oxide layer also plays an important role. It was in the slide where we discuss about the origin of PMA, the hybridization. So, all this depend on oxide layer. Okay. So, when this work was published, I asked my student to try tantalum cobalt iron boron multilayer to see whether she can get perpendicular anisotropy. Okay, but we did not get. Okay. So, this implies that this oxide layer also plays an important role. So, all these are important. So, you need a tantalum or some suitable seed layer, and you need a thin cobalt iron boron, this is important. You also need magnesium oxide. All these 3 layers play an important role. So, the correct answer is 4. Okay, so, now let us move on to the next design. So, first design is IPMA. So, we have interface PMA. Okay, people are not happy with what they have, right. So, from 60 nanometer in plane MRAM, you can bring down to 40 nanometer MRAM based on the interface PMA concept. But the technology has to grow better, right. So, we want to make even smaller from 40 nanometer MRAM, can we shrink down to say 28 nanometer or something like that. Okay. So, people always try to improve the technology, that is where the researchers come in, right. So, for this particular concept, we cannot increase the thickness. So, in the interface PMA, you cannot increase the thickness. So, we know that KUV is the anisotropy constant, right. So, if you increase the thickness, you can increase volume, but in the case of interface PMA, you know that if you increase the thickness of cobalt iron boron, magnetization will go from perpendicular direction to in plane. So, you cannot just increase the thickness of cobalt iron boron. Okay, but if you want to increase the volume of the device, you can come up with some creative idea like this. Okay, so, instead of having one tantalum layer and one magnesium oxide and one cobalt iron boron, this configuration smartly introduces 2 interfaces of tantalum cobalt iron boron magnesium oxide. By introducing one tantalum layer in the center, okay, we have one tantalum layer here, 2 cobalt iron boron layers, and we have 2 magnesium oxide layer. Okay. Okay, so, this is the normal IPMA interface. You have tantalum, cobalt iron boron, magnesium oxide, whereas in the dual IPMA structure, you have only one tantalum which is in the center. Then if you look at this way, you have a tantalum, cobalt iron boron, magnesium oxide. If you look from here, you have another tantalum, cobalt iron boron, magnesium oxide. Okay, so now you have two magnesium oxide layers. Basically, you are now doubling the volume, right. So, you have two layers storing information. So, you can basically double the volume. So, that is the idea of this dual perpendicular magnetic tunnel junction. Okay, so, with this particular concept, people can achieve 28 nanometer diameter MRAM. Okay. So, because you have increased the volume, you made now you have two layers. So, your thermal stability is increased, and they also people also found that for same writing current, thermal stability is higher. Okay. That is one thing. Then one fine aspect of this particular design is when you read information, these three layers play an important role. Okay. So, here you need to have optimum thickness of magnesium oxide for achieving high TMR. Okay. But here you can make very thin magnesium oxide, because here you are just creating an interface to get perpendicular magnetic anisotropy. So, for the bottom side they will use thinner magnesium oxide, okay, because here your magnesium oxide is not useful for reading, you just want to have this interface to get perpendicular magnetic anisotropy. So, they make the MgO thinner. Okay, so, these are the fine aspects of this particular design. Any question? So, what magnetic material you suggest besides cobalt and boron? You tell me, Moditma.
Asked to re-explain some concepts.
Writing energy being more in plane MRAM compared to perpendicular MRAM with respect to the difference between HP and HK. Okay, I will come to that. But Moditma, answer my question. What other material you want other than cobalt and boron?
So this boron is basically very small and non-magnetic, right?
Yeah.
So is it kind of a doping only?
Yeah, it's a doping, yes.
So usually it will can give a secondary phase at the gate point.
Okay, this cobalt iron boron, when you sputter, it is amorphous. Okay, so when you make MRAM, this cobalt iron boron is deposited as an amorphous layer, but in the MRAM process, they will do some annealing. Okay, after they deposit all these layers, they will do some annealing at around 300 degrees Celsius. So, during this annealing, this this boron will go somewhere to the tantalum layer or some other layer. So, boron will diffuse. So, you will have a crystalline cobalt iron layer. Okay. So, the final result is a cobalt iron crystal. Boron will diffuse. So, why not iron, cobalt or other magnetic alloys? So, what
She answered the I think she answered the question.
Okay. Okay. So, today I presented a very coherent story of people looking at many different materials, then finally arriving at iron, cobalt, boron. Okay. So, I told you cobalt platinum has problem, terbium iron cobalt has problem, iron platinum has problem. Then I told you why cobalt iron boron is interesting, why it is useful. Okay. So, this question should not come. Okay. So, people look at various materials based on their properties, then they finally arrive at cobalt iron boron. So, I told you a coherent story today. Okay, that is my answer. What is the other question?
To re-explain
okay, between HP and HK. When we are talking about in plane materials, in plane MRAM materials, so their anisotropy field is very low. Okay, their anisotropy field is around 50 Oersted or 100 Oersted. Okay. But if you look at the field, the perpendicular, I mean the field you need to keep the magnetization in the perpendicular direction, that field can be like 10,000 Oersted, something like that. Okay. So, I told you during the precession motion of magnetization going from one side to the other direction. So, the precession happen, then the magnetization is spending a long time in the perpendicular direction, which means we need to apply this field for quite large number of time. Okay. So, you see the difference, anisotropy field is only 100 Oersted and you are applying 10,000 Oersted kind of field to switch. Okay. So, this is the difference. So, your HK and HP are quite different in plane MRAM materials. Okay. On the other hand, in the case of perpendicular material, the HK is around, let us say 5,000 or 10,000 Oersted. So, this is the field that helps to retain information, retain or store information. What happened? Okay. Okay, so, in this case when you switch magnetization, so I told you this is like a Stoner-Wohlforth particle. So, this is HK, right. So, easy direction is perpendicular, hard direction is in plane. So, even if your magnetization is going from perpendicular to one direction to the other direction through the in plane direction, basically the hard direction field is same as HK in this case. Okay. So, you do not spend extra energy to switch information.
In this scenario, how will be the energy barrier for the two in plane and out of plane? Which one will have a higher energy barrier?
I mean, so when you are talking about this, right, what does the energy barrier mean? So, say you have in plane, I mean, okay, sorry, let me redraw this. So, when we draw the energy barrier diagram, what is your y axis, sorry, x axis?
Maybe the angle.
Yeah, so it's the angle, right? So, let us say this is one easy direction, this is other easy direction. So, this is the energy at a hard direction. Okay, so, hard direction the energy is high, it is not stable. So, energy barrier is basically this, right. So, you cannot talk about energy barrier in the hard direction. Hard direction there is no energy barrier, it is at the highest energy.
Yes, but in
Mhm.
we are having an energy barrier, and in plane configuration we will also have an energy barrier.
Yeah.
I just want to know which one is the higher energy.
Okay, so you are comparing between this and this, right? So this is what I mentioned a few minutes ago. So this case, okay, if you convert this into HK, okay, which is 2 Ku over Ms. So this in terms of field value, this can be like 10,000 Oersted. Okay. In the case of in plane material, this HK is only around 100 Oersted. Okay, so it's much low. Okay, now let us move on to the last concept. Okay, so for in plane we had 60 nanometer limit, in plane 60 nanometer limit. Then for the IPMA we had like 35 nanometer limit. Then with the dual IPMA we had like 28 nanometer kind of diameter. So, people are looking at whether we can go even below 28 nanometer. Okay. So, in that connection they proposed a concept called nano MTJ. Okay. So, this nano MTJ combines two anisotropy. Okay. One is the shape anisotropy plus the interface anisotropy. Okay. This nano MTJ makes use of both shape and interface anisotropy. Okay. So, if you look at the sample here, so they have some kind of tantalum kind of layer, then a ferromagnetic layer and a magnesium oxide. Okay. But this layer is very thick, okay, so around 15 nanometer. Okay, so this layer we know that when the magnetic layer is very thick, magnetization has to be in plane. Okay, so if you grow a film like this layer will have in plane magnetization. But in this study what they have done is they made lithography in such a way that they can make a kind of cylinder. Okay. So, we know that when we have a cylinder, the z axis is in the perpendicular direction, I mean along the length direction. So, because they made this so small, because of the shape anisotropy, this magnetization is now pointing in the up direction. Okay. So, this is called nano MTJ, because they are making MRAM devices now in the 5 nanometer, 10 nanometer kind of range. So, this is called nano MTJ here because of the shape anisotropy. So, you see that this is like a perpendicular, I mean cylindrical shape, right. Because of this shape the magnetization is in the perpendicular direction. Okay. So, this is again from Tohoku University. So, they measure hysteresis loop in the perpendicular direction, then they observe perpendicular hysteresis loop for 4 nanometer diameter, 7 nanometer, 11, 15, all these small diameters they can observe perpendicular hysteresis loop. And in MRAM community they use the symbol delta to represent KUV by KBT, thermal stability. So, when you see delta is around 80, what it means is that KUV by KBT is around 80, which means data can be stored for around 10 years, more than 10 years. Okay, so, now the next step to go below 28 nanometer, for example, even 4 nanometer MRAM can be achieved using this nano MTJ design. Okay, let us do some questions. Okay, majority of you are wrong. So, two interfaces of cobalt and boron will look something like this, right? Can this give PMA? It cannot. Okay. So, this is wrong. We need this everything. I told you that seed layer is important, magnesium oxide is important, and this being thinner is also important. All these are important. So, this is the correct answer. This or this are wrong answer. Okay, let us skip this one. Let us go to the last slide. Okay, so far we have been only learning about the free layers. So, the free layer can be tantalum, cobalt and boron, magnesium oxide, or it can be a dual PMTJ. So, we have been focusing only on this layer, but I haven't told you how the whole stack of MRAM will look like. Okay, so, the free layer is at the top in this particular design. Okay, then we have some magnesium oxide. Okay. Then this whole thing starting from that blue layer on top all the way here is called the reference layer. Okay, so you notice that there is a thin cobalt and boron layer at the top. The reason I will explain later. Okay, there is a thin cobalt and boron at the top, which I will explain tomorrow. Okay. So, today you just take this for granted. The main aspect of the reference layer is this cobalt platinum multilayer in the synthetic antiferromagnetic structure. Okay, so, we learnt about this synthetic antiferromagnetic structure. The two magnetizations are pointing in antiparallel direction. So, this helps to reduce stray magnetic field from the reference layer. Okay, so, in the perpendicular MRAM technology, we are using cobalt platinum multilayers as the reference layer material. Okay, so, these multilayers have a very large anisotropy field or anisotropy constant. So, the HK of these materials can be as high as 20,000 Oersted. So, during the read or write operation, this magnetization will not be switched. Okay. So, the reference layer magnetization is always fixed. Fixed because of the high anisotropy. Okay. These materials have very large anisotropy, we do not need to switch them during the reading or writing operation. So, they are always fixed. Okay, so that is why we use cobalt palladium of cobalt platinum multilayers. Okay, so this is how the reference layer will look like. And to induce this synthetic antiferromagnetism, people use either ruthenium or iridium. Okay, so this is the last slide. Any questions? Okay, if you think we are learning too many things, it's better you watch the YouTube video at night. Okay. So, YouTube videos are streamed every day, right. So, today's video will be available in a few minutes. So, at night you go through the recording, otherwise like too much information all may be going above your head. Okay. So, please watch and reinforce the concepts. Yeah. Okay.
Practically doing this big hydrostructure, how are they done? I mean, in single sputtering system, all these many targets are put on them.
Okay.
I mean, a number of layers.
Yeah, yeah. So, the industry sputtering system usually will have a few chambers, at least 2 chambers. Okay. Some machine may have 3 chambers. So, usually they will have 1 chamber for oxide deposition. For example, magnesium oxide you want to deposit. So, there will be a dedicated chamber where you deposit magnesium oxide. Let us say you deposit cobalt, platinum, cobalt iron boron and say tantalum. So, there will be 1 chamber for such targets. So, what happens during the fabrication of this whole stack? So, let us say we start with the tantalum. So, tantalum will be sputtered, then cobalt gets the wafer will move from this place to this place, cobalt will be sputtered, the next layer platinum. So, the wafer will move to platinum, it will get sputtered, then it will come back to cobalt. So, there will be a lot of back and forth oscillation. So, many of these multilayers will be sputtered, and let us say we have ruthenium here. So, when you want to deposit ruthenium, the wafer will move here, ruthenium will be deposited and so on. So, after everything until here is deposited, then this wafer will move to the magnesium oxide chamber, magnesium oxide will get deposited, then it will come back, then the remaining layers will be deposited. So, it is like, so there will be 2 or 3 chambers to answer your question. Yes. And this transfer all happen in vacuum. Okay. So, when it goes from this side to the other side, vacuum is not broken. So, the chambers will have base pressures of 10 power minus 8 or minus 9 torr. So, wafer does not come out until everything is finished, all the layers must be sputtered, only then the wafer comes out. Any other questions? No, okay.
Sir? Hello, sir.
Yeah.
Sir, what could be the ratio of the, I mean, the MGO thickness in dual PMTJ?
Okay, the ratio of the MGO thickness in dual MTJ. Sorry. So, you are talking about this one, is it? So, in the case of TMR, right, when you want to read information we design MGO thickness to be around 1 nanometer, maybe plus or minus 0.2 nanometer we can say. So, this is the thickness of magnesium oxide here. So, here if you make the magnesium oxide too thin, you may have pinholes. So, some region magnesium oxide may not be sputtered. So, you will have pinhole, there will be no tunneling. So, TMR will be affected. So, to ensure that you have reasonable TMR, the magnesium oxide here will be around 1 nanometer. But in this at this position, you do not need to make that magnesium oxide very thick. So, maybe it is around 0.6 nanometer or 5 nanometer. I do not know the exact value, but I am just guessing that it could be around 0.6 nanometer.
Sir, I have one more question. Recent research on dual PMTJ, they tell that thinner top MGO barrier is used and thicker bottom MGO barrier is used for a PMTJ in order to maintain the PMA and TMI. So, how is that feasible?
Okay, whether it is bottom or top, it depends on how you design your MRAM. So, in this particular case, my free layer is at the bottom, okay, reference layer is at the top. So, in that case, this layer has to be thicker, but if they design with the free layer on top, reference layer at the bottom, right, then this MGO has to be thick. Okay. So, do not use the terminology like bottom magnesium oxide, top magnesium oxide, just refer to the magnesium oxide that is at the interface between free layer and the reference layer. Yeah.
Thank you, sir.
Okay, thank you. Okay, if there are no questions, we end here. Thank you.
Students are asking for slides.
Yeah, I will send. Lagos.